Okay, so now let's look at an example where we use the definition to evaluate a limit at infinity. So in this example, we look at the limit as x goes to infinity of the function 2x over x plus 1. Right, and we're going to prove that this limit is 2. And so just to reduce the amount of writing we have to do, let's introduce the function f of x as 2x over x plus 1. Okay. And again, we're going to start off by trying to find some sort of estimate for f minus l. So in this case, f minus 2. And we note that this function isn't defined at x equals minus 1. And because we're taking a limit as x goes to infinity, right, we can, from the start, only look at values of x bigger than minus 1. Right. So that we don't have to worry about that point where the function isn't defined. Right. So for x bigger than minus 1, right, we start off trying to find a nice estimate for this f minus 2. Right. And in this case, that's 2x over x plus 1 minus 2. Right. Adding the fractions, we get 2x minus 2x minus 2 over x plus 1. Right. And you see the two x's cancel, we get absolute value minus 2 over x plus 1. And because x is bigger than minus 1, x minus 1 will be positive. So that absolute value just becomes 2 over x plus 1. We call this equation A. Okay. So now this equation tells us how to pick our m. Right. So, unlike the case when you're looking at a limit at a point, right, it's not always very straightforward to see how you should pick your m here. Right. So, let's do a bit of rough work. Right. So this isn't part of your solution. Right? This is just, your little workings out on the rough page. Right, so what we want is 2 over x plus 1 to be less than epsilon. Right? So multiplying by x plus 1, which remember is positive because x is bigger than minus 1, we get 2 less than epsilon x plus 1, or then epsilon x bigger than 2 minus epsilon, or then x bigger than 2 over epsilon minus 1. Okay. So this is how we should pick our m. We should pick our m as 2 over epsilon minus 1. Right. So this was rough work, so we're not going to include this in our solution. Right. So now we say, well, fix epsilon bigger than 0, and let m be 2 over epsilon minus 1. Okay. So now we're just replicating the definition. So we have to see what happens if x is bigger than m. Well, if x is bigger than m, then x is bigger than minus 1, right? Because m is minus 1 plus a positive number. Right? So m bigger than minus 1. Right? Now why do we need that? Because remember, in deriving this equation, we assumed that x was bigger than minus 1. Right? So we have to show that we can use this equation. Right? So because x is bigger than 1, by a, we see that f of x minus 2 is 2 over x plus 1. That will be less than 2 over n plus 1, right? Because x is bigger than m. And this is 2 over epsilon minus 1 plus 1, which gives you epsilon. Alright. So, this is exactly what we wanted to prove. For any epsilon bigger than 0, there is an m, and we found it, so that if x is bigger than m, then absolute value f of x minus 2 is less than epsilon. Right. This is true for all epsilon bigger than 0. So by the definition of a limit at infinity, we see that the limit as x goes to infinity of this function f of x is 2. Yeah. And again, all your examples will follow more or less the same pattern. Right? Starting by trying to find this estimate, and that could be more difficult depending on how complicated the function is. Right? And then we just replicate the definition. Right. So we'll look at one more example, and hopefully then you'll be comfortable with this kind of problem.
Okay.